Hi everyone, I will revise with you now all the required KPIs for your system-wide quiz. Remember that system-wide quiz 2 has the following KPIs. You have KPIs 8.6 and 8.7 and 8.8. And in section 9 you have KPIs from 9.1 to 9.7. I will start with you now revising the from 8.6 to 8.8. This part is explaining Dalton's atomic theory. So we are going to explain now Dalton's atomic theory. This is KPI 8.6. Here you need to list the main points of Dalton's atomic theory. What are those? First, matter is composed of atoms that are indivisible and indestructible. Indivisible means that you cannot divide, and indestructible means that you cannot destruct it, so you cannot damage an atom. 2, atoms of an element are identical. Identical in what? Identical in size, mass, and chemical properties. 3, atoms of an element are different from atoms of another element. 4, different atoms combine in a given ratio. We call it a whole number ratio to form compounds. Number 5, in chemical reactions, only atoms rearranged, separated, combined, but they never changed. This KPI you should be able to compare and contrast. Democritus atom or atomic model and Dalton's atomic model. In order to compare and contrast Democritus atom with Dalton atom, you need to look for similarities and then for the differences. For similarities means what's common in both models. First, matter is composed of atoms. Both of them believed in atoms. 2, atoms are indivisible and indestructible. 3, changes in matter are due to changes in grouping of atoms, in the rearrangement of atoms, due to change in grouping. While there are many differences between the model, Democritus stated that matter is composed of empty space. So matter is an empty space, like just a space, nothing is there, while atoms move in the space as solid particles. Dalton states that atoms combine to form compounds, new compounds. They are not described by Democritus. Remember that also Democritus believed in the atoms and that the movement, shape, and size of atoms determine their properties. In this KPI, we are going to compare different models that led to discovery of the subatomic particles. Remember, subatomic particles are the small particles existing inside the atom, including protons, neutrons, and electrons. In this video, I'm not going to describe in details the experiments done by every scientist. You can go to the previous video to discuss it. Here, I'm just recapping the work done by Thomson, Rutherford, and Millikan. Thomson put a model for the atom called plum-pudding model. This model described the atom as a watermelon or plum pudding, where the electrons are found in all atoms. Atom is spherical, and the positively charged particles are evenly distributed, like they are everywhere in the atom, and the electrons are embedded between the negatively charged particles. This is according to Thomson. Also, Thomson has done an experiment, we call it cathode ray experiment. He used cathode rays inside a cathode ray tube. By using this tube, he was able to measure the effect of magnetic and electric field on the path of the ray. And he was able to determine the mass to charge ratio of particles. Mass to charge ratio means the ratio between the mass and the charge of the particles. And he concluded that cathode ray contains negatively charged particles. Those particles, we call them electrons. Rutherford made an experiment. We call it gold foil scattering model. By doing this experiment, he was able to conclude that most of the atomic mass is concentrated in its nucleus. Nucleus takes a very small space in the atom. So if we say that the atom is so huge, the nucleus just occupies a very small part in its center. And this means that most of the atom is a vacant space. So the atomic mass is concentrated here in this very small part, which we call it nucleus. It takes a very small part of the atom. The nucleus is dense and small, It contains all the positive charge and the most of the atomic mass. Almost all the atomic mass is existing inside the nucleus. So nucleus is the center of the positive charge. Electrons are found in the empty space around the nucleus. This is according to Rutherford. Millikan has done an experiment using oil drop, and he let the oil drop to fall with an electric field. He confirmed that the negative charge of the electron, has a negative charge, and also he was able to determine the mass of the electron. So he concluded the mass and charge of the electron using the charged oil particles. In the next slide, you are going to know in detail the results of Millikan's experiment. Looking up here is the experiment, the model of the experiment done by Millikan. He used an electric field which has positive and negative charge. He used a source of ionizing radiation, that create ions in the field inside. And here we have a microscope. By the microscope, he was able to view the falling or the movement of the oil droplets. On connecting those plates, these are two plates, he connected them with a positive and negative pole. He was able to charge the plate. So the plate becomes charged. When the oil droplets fall between the plates, he was found that some of the droplets fall slow or fast or rise or pause, depending on the strength of the electric field he used. By this experiment, he was able to measure the charge and the mass of those particles. He found that the oil particles have been covered with charged particles. Once they are charged, they started to rise up. By calculating the charge and the mass collected over the particles, he was able to calculate the mass of the particle and its charge. He found that the charges are always a multiple of a constant number. He named this number the charge of the electron. Also, he found that the mass of those particles usually a multiple of a constant number. This number was the mass of the electron. So, to conclude, Millikan determined the mass and the charge of the electron using oil droplets. This is very important information you should know. The movement of the oil droplets, up or down or pausing, slow or fast, depends on the charge of the droplets and depends on the strength of the electric field he used. We will start now in section 9. Section 9 is going to learn here the number of the protons and the mass number, that are used to define an atom. In order to define any atom, you need to learn two numbers: atomic number, which is designated by letter Z, and the mass number, which is designated by letter A of an atom. We expect here that X is the symbol for the atom, Z is the atomic number, and A is its mass number. What is atomic number? Atomic number is the number of the protons in the nucleus of an atom. All of you know that the atom has positively charged particles, we call them protons. The number of those protons determine the identity of the atom or its atomic number. While the number which we usually write below the symbol of the element is its mass number. What is the mass number? Mass number is the sum of the protons and neutrons in the nucleus of an atom. So the number of protons is the mass number, atomic number, while the number of protons and the neutrons is the mass number. Here, you should be able to calculate the number of neutrons. If you need to calculate the number of neutrons, you should subtract the atomic number from mass number. So mass number minus atomic number. Or I can say A minus Z. You are going to get the number of neutrons in each atom. Sometimes the number of neutrons equal the number of protons, and sometimes it's higher. You are going to learn more about this in the coming slides. The next KPI is to explain how the type of the atom is determined, how to identify the type of an atom. Type of an atom is identified only by its atomic number. So you know that carbon is carbon because it has 6 protons. You know that nitrogen is nitrogen because it has 7 protons. So the number of protons is critical to know the type of the atom. It is not the number of the electrons and it is not the number of neutrons. Some atoms may have more or less neutrons and some atoms may gain or lose electrons. But the number of the proton is the identity of the atom. This KPI, you should practice the mass number, atomic number, number of subatomic particles in some atoms. I wrote here like 3 or 4 atoms, and as example you can practice more. Question 1, Mg, the symbol for magnesium atom, 1224. Very simply, the small number is the atomic number, and the big number is its mass number. Number of neutrons you should subtract mass number minus atomic number. So 24 minus 12 equals 12. Number of protons, it is the atomic number itself. Number of the electron, if the atom is neutral like that, so it's also 12. Because in neutral atom, the number of protons equals the number of electrons. Remember that. Calcium 2040, atomic number is the small number 20, the mass number is 40, the number of neutrons 40 minus 20, number of protons equal the atomic number, and the number of electrons also equal the atomic number. Here, arsenic 3375, atomic number 33, mass number 75. To calculate the number of neutrons, you need to subtract 75 minus 33. The number of neutrons here equal 42. Number of protons, and here is the number of electrons. In this atom Br3580, atomic number is 35, mass number 80, number of neutrons, also you need to subtract 80 minus 35, the answer is 45. 45. Number of protons, and here is the number of electrons. Radon 86,222. So the proton number or atomic number is 86, electron number is 86, mass number is 222, and the number of neutrons, by subtracting it, the number is 136. KPI 9.4, you should define isotopes, determine atomic number, mass number, and the subatomic particles. First, we need to learn what are isotopes. Isotopes are atoms of the same element that has the same atomic number but different mass number, or we can say different number of neutrons. Because as you know, the mass number equals the sum of protons and neutrons. If the number of protons doesn't change, because the proton is the atomic number, so any change in the mass number will be only due to change in the number of neutrons. Almost every element in the periodic table has many isotopes. Let's take some examples. Here we have 3 isotopes for carbon, C12, C13 and C14. What is the atomic number? You will look for the atomic number of carbon in the periodic table. You will find it 6. In any isotope, it doesn't change. This number also doesn't change for the electrons, 6, because it's a neutral atom. For proton, it's 6. The mass number here is 12, 13, and 14. So in calculating the number of neutrons in each isotope, in carbon 12 isotope, it's 12 minus 6, 6. Here, 13 minus 6, 7. 13 minus 6, 7. And 14 minus 6, 8. So the number of neutrons are different. So different types of isotope is only due to the different number of neutrons. Also, hydrogen has 3 isotopes, H1, H2, and H3. The atomic number, looking up the atomic number of the hydrogen in periodic table, it's 1. Mass number, 1, 2, 3. Number of electrons, it equals the atomic number and the proton as well, while the number of neutrons will be different. In H11, the number of neutrons 1 minus 1, 0. Here 2 minus 1, 1, and 3 minus 1, 2. Remember that the position of the element in periodic table is only 1. So if you have H11 or H12 or H13, all of them will occupy the same position of the periodic table. We have only one box for hydrogen. So how can we represent those isotopes in one box? There is only one way to do that. You are going to learn about it in the next slide. Explain why isotopes have similar chemical properties. They have similar chemical properties very simply because they have the same number of electrons. Because the number of electrons determine the reactivity and the chemical reaction of any element. So in order to calculate the average atomic mass, you are going to multiply the mass number of each isotope by its abundance and add them all, then divide the final answer by 100. Let's take an example. If chlorine has isotope, first isotope is Cl35, the second isotope is Cl37. Expecting that the percent abundance of the first isotope is 75.77%, and of the isotope Cl37 is 24.23%. How to calculate average atomic mass? First, look for the mass number. The mass number here is 35, while in this isotope is 37. What's left is to calculate the average atomic mass. First, calculate the percent abundance. calculate the percent abundance of the atomic mass of each isotope, and then add them all. So here I will write 75.77 multiply 35. Get this answer first, and then 24.23 multiply 37. Get this answer. Then to calculate average atomic mass, you are going to add the answers you got, divide by 100. So you are going to get the final answer. The answer of the first question after calculation is Let's solve some questions on average atomic mass calculation. Question 1. Rubidium has two isotopes, Rb85 and Rb87. If the abundance of rubidium-85 is 72.2% and the abundance of rubidium-87 is 27.8%, what is the average atomic mass of rubidium? You just apply the formula. Average atomic mass equal the mass number of each isotope multiplied by its abundance. Second isotope 87 and its abundance is 27.8 and divide all by 100. So you will get the answer 85.556 atomic mass unit. This is the unit of average atomic mass. Let's do the second example. Uranium has three common isotopes. If the abundance of uranium-234 is 0.01% and the abundance of uranium-235 is 0.71% and the abundance of U-238 is 99.28%, what is the average atomic mass of uranium? Average atomic mass equal the mass number multiplied by the abundance of each isotope. 2, 3, 4 multiply 0.01 plus the second isotope mass number multiplied by its abundance. 2, 3, 5 multiply 0.71 plus 238 multiplied by the abundance 99.28, and all these calculations should be divided by 100. You will get the answer 237.98. Very simply, you can get the answer ready from the periodic table, but sometimes the number of decimal places or significant figures are different. So you should make the calculation first and then look up the answer in the periodic table, because the atomic mass, the average atomic mass, is the number which is given in the periodic table. Third example, titanium has 5 common isotopes, and you are given the mass number and the abundance of each isotope and asked to calculate average atomic mass of titanium. Average atomic mass equal 46 multiply 8 plus 47 multiply 7.8 plus 48 multiply 73.4 plus 49 multiply 5.5 plus 50 multiply 5.3. When you do this calculation in the exam, do each calculation separate, like 46 multiply 8 first, 47 multiply 7.8 first. Do each calculation and then add them all and divide the result by 100. You will get the final answer. Final answer is 47.92 atomic mass unit. Last question is a challenging question. It's asking why atoms have different isotopes, or how is that helium, for example, can exist in 3 different forms. You'll find the answer in the next slide. Here you'll find the answer of challenging question.